Using insertion view, in this part, we will use our insertion idea to solve some special sorting problem. But our goal here, the goal is to use the minimum number of comparisons to sort an array with relatively small sizes. All right, so first, I like to, discuss the general idea. So then we try to solve a few problems. Insertion with binary search. Here, it sounds familiar, right? So I mentioned a little bit this topic before. Right? Now, we need to use this idea. So let me review a little bit in our insertion sort. So remember, we do two steps. The first step, search step. All right, search step. Second, shift operation, right? We need to do these two steps. All right. Now, in the search step, I mentioned before, there are two different ways we can do. One way, linear search. Another way, binary search. All right. So here, there is a question. In our standard insertion sort, we use the linear search. We didn't use the binary search. And we know, everyone knows, the binary search can do better than the linear search, right? Why we do not use the binary search? The reason is simple, because we need to use shift operations. When we need to use shift operations, then the benefit of the binary search is reduced to the minimum. Because the most of the work you need to do at the binary search. So think about this. Suppose there are k elements, right? K elements in a current array. In order to do the linear search, we need to use this number of comparisons. In order to the binary search, we need to use this number of comparisons. Okay? Then, after that, we need to do the shift operations, so we need this many comparisons. So you can see, even you save a lot here, but after that, you still need to pay this much to complete the whole insertion sort. So the gain is very little. So for that reason, so then people just, forget about the binary search in the insertion sort. All right, so that's the story in the standard insertion sort. Okay, standard insertion sort. Now, we consider special situations. So not standard. Special cases. Okay, we consider. So what kind of special case? From the above analysis, you can see the problem mainly occurs at this shift operations. So in other words, if there is no shift operation, if under some special situation there is no shift operation, then the benefit of binary search is big. Right? Think about this. If under some very special situation, we do not need to do that shift operations, then there is no doubt everyone will pick binary search in the search step. Yeah. So that conclusion is very simple, very straightforward. Yeah. But you may ask the question like this: under what situation you do not need to do shift operations, right? Under what situation you do not need to do shift operations? Yeah. All right, so here, let me describe some special situations you do not need to do shift operations. Yeah. All right, so let's look at the first example. The first one. Sort a 3-element array. Three-element array. How about that? Only 3 elements in the array. Okay? So why in this case we do not need to show? Yeah, because first, this number is very small. Okay? A small number. Yeah. Only 3 elements in the array, right? Yeah. 3 elements. Then we have 3 locations. Right? 3 locations. Yeah. X0, X1, X2. Okay? When we sort, we only need to find what is the smallest element, what is the largest element, what is in the middle, in which, when we do this, we can avoid shifting operation. Why we need to do shift? Okay? We can use other temporary variables. Why we need to do shift? Right? Small number, we don't need to do shift. Yeah. The reason we want to shift in the standard insertion because we want to sort the general n-element array. N-element array, the size could be very large. We cannot, really arrange specific elements for large number. It's very hard to control individual elements. So we use, this shifting way we can organize our data. So that's the reason. But for small number of elements, we do not need to really using special operations to organize data, right? So that's the main difference. Yeah. All right. For this simple, actually, we just use the insertion sort. Yeah. So let's look at the worst case. Worst case, sorting 3-element array. Okay. Yeah. All right. X0, the first element. Yeah. No comparison needed. Then X1. To get it sorted, we need one comparison. Okay? Yeah. One comparison between X0 and X1. All right. Then X2, the worst case, you need to compare both. So two more. Okay? So the total number comparison, 1 plus 2 equals 3. Yeah. All right. So we're fine with this result. 3 comparisons needed to sort whole 3-element array. So we're fine with it, with this result. All right, we're fine with this result. All right. Next, we want to go to next sorting problem. Yeah. Sort 4-element array. How about that? 4-element array. How about that? Okay. All right. Okay. X0, X1, X2, X3. What is the minimum number of comparisons? So we need minimum number of comparisons for worst case. Not just minimum, but also for the worst case, not for the best case. Worst case. Yeah. All right. So now, let's do it this way. Okay. Yeah. First, we already solved sorting 3-element array with 3 comparisons, right? So let us just still do it. Okay. Sort 3-element array with 3 comparisons. All right, yeah, the first step. Then the next x4. All right, next 4. Yeah. Now we need to consider 2 ways. All right, so the first way, standard insertion. If we use the standard insertion way, so that is 1, 2, 3, right? Worst case, you need a 3. So you need 3 more, right? 3 more. Okay? So the total, the answer, 3 plus 3 is 6. The answer total, 3 total number of comparisons. Yeah. All right. So now we do not use standard insertion. Okay? Yeah. We use the binary type insertion. All right. So this time, now, let's go back to our discussion at the beginning. Yeah. This time, because the number of elements is small, 4, we do not need to worry about shifting operation, right? Why we don't need to do shifting. Okay? In that way, we can choose binary search to save some comparisons. Okay, all right, so let's do it. All right. Compare x4 with the 1 in the middle. Binary, so you always compare the element in the middle. So compare x4 and x1. So that is your first comparison, right? Yeah. There are only 2 cases. Greater than x1, less than x1, right? So if it's greater than x1, you compare with x2, another comparison. Okay? If it is less than x1, you compare it with x0, also another comparison, right? Because these 2 cases, you only need to take one of the 2 cases. You do not need to do both cases, right? So in that way, actually you just needed 2 more comparison, and the total number of, because you need to add the first 3, the total number of comparisons, 5. You can see you save 1 comparison with, comparing with standard insertion. You save one comparison. You do better. Yeah. The reason, because think about, there is no shift operation. Here, why we need a shift operation? We compare it with x1. If statement, if greater than x1, we compare with x2. Based on the result, we can write the sorted array in order, right? Yeah, certain given order. Things like that. Why we need a shift operation? We don't need a shift operation. For the small number of elements, okay, usually relatively small. Okay? Yeah. So in our program, we can explicitly write the elements in order easily, right? We don't need to use for loop. So you can see that's the special situation we can take advantage of, eliminating the shift operations and use the binary search to improve our sorting efficiency. Okay, try to get this idea. Yeah, so here. All right. With this same approach, so think about, can we use this method to sort? So the next, we need to sort 5-element array. 5-element array. Okay, so our next step. Yeah. But this problem much harder than the previous. Yeah. Much harder. Yeah. Okay. So let me just use another video to solve this problem. They're much more complicated. So we need another video to explain the details. Very challenging. Very challenging. All right, so let me finish this one first.